Good afternoon, everyone, and welcome to the ninth problem solving session for the course Fundamental of Semiconductor Devices NOC24E02, hosted by NPTEL. My name is Amit, and I'm a PhD student at ISC Bangalore. Quick summary from the previous sessions. Firstly, we talked about the classification of materials in terms of their electrical conductivity, which we gave in terms of sigma. We saw what are metals which have high electrical conductivity, insulators which have low. Semiconductors have somewhere in between. However, a very unique property of the semiconductors we saw was that their conductivity was tunable. And then we saw the via the band gap, this entity called the band gap in a semiconductor, which is essentially when a large number of let's say semiconductor atoms are coming together to form a lattice, what happens is that their orbitals overlap, and rather than having a fixed energy, what we have is a band of energy. So for instance, electrons can occupy all these states above energy level EC and below this energy level EV. However, this gap that you see, this is the forbidden energy gap, also known as the band gap. And you can also excite the electrons from the bottom of valence band to the top of conduction band by, let's say, shining a light. On the other hand, electron can also fall back from conduction band to valence band and thus in the process emit a photon. LED does exactly that. Then we saw another strong entity called the effective mass. So to understand that, we saw that the electron that is traveling inside the lattice, it's not it experiences a periodic potential due to the periodicity of the lattice. We denoted it using something like this. So these are the potentials that an electron experiences. The electron is not free, so to speak, and the same we can draw it, the energy of this electron which is experiencing this periodic potential under the Ronick-Penny model, which we talked about. We demonstrated in terms of the EK. The energy versus k is a wave vector given by 2 pi by lambda, and we saw that the electronic energy now can be written. This diagram is, by the way, E versus k is on the band structure. Again, the conduction band energy EC and the valence band energy EV, and again you see this, the difference between the minima of conduction band and the maximum valence band is the forbidden energy gap EG, and here there are many states in the EV and also in EC. These states are so close that they effectively form a continuum, and the curvature that you see of this conduction band and valence band effectively gives you the effective mass for conduction band electrons, and for valence band it gives for holes. This effective mass is a very powerful entity in the sense that now we can ignore the quantum mechanical effect, so to speak, and you can strictly, wherever the mass comes, we can use the Newtonian mechanics. So when we say F equal to ma, force equal to mass into acceleration, their mass m is not the rest mass of electron 9.1 10 to the power minus 31. The effective mass is, the effective mass, as you can predict, depends on the periodic potential and other factors, which essentially depends on the nature of the material, the nature of the semiconductor that we are talking about. Finally, as I mentioned, that we have these energy states which are over there, and we saw in a 3D system we defined an entity called the density of states, given by this symbol dE. Density of states is essentially the number of energy states per unit energy, per unit time, per unit energy per unit volume, which gives us density, and we saw it's directly proportional to the energy of the level that we are talking about. And these, as I told you, for EC we have the energy states of electrons, and these are the, in valence band we have the energy states of holes. Now the other entity that we talked about was the Fermi function. So Fermi function is nothing but the probability of finding an electron in any given energy state. So let's say this energy state is E1. So where does this, is the electron occupying this energy state or not? That was given by Fermi function, and we saw that it was given by something like this. EF is the Fermi level, an analytical concept in the sense that whether finding the probability of an electron is exactly half. If you go above Fermi level, then your probability decreases below half, and at absolute zero temperature by kT, at absolute zero, and at absolute zero, as you can see, this term will increase, and above E and F you see a perfect rectangle, as we had seen. This is a probability distribution function, as we had talked about, and there are multiple, so there are degeneracy. This means there's not just two electrons, multiple electrons can occupy, because there are multiple, the same level, but it's a degeneracy. Okay, and then we can obtain the carrier concentration at equilibrium. So for instance, that was given by N, and if you integrate the density of states, that is the total number of states available per unit volume per unit energy, and multiply the probability and then integrate it in any differential element. This is from EC to infinity because we're talking about electrons. For holes it will be minus infinity to EV, and we saw that this making some assumption, this comes something like this. Here EC is the conduction band energy, EF is the Fermi level, right? And this is the effective density of states function, and for similarly we saw for holes. Now the strongest part of a semiconductor, as I've been saying, was the thing that we can dope it. That means we can add some impurities. So for instance, for a typical semiconductor, for an intrinsic semiconductor without any doping, the Fermi level will lie exactly at the mid band gap here. For a semiconductor which is doped N type, what we see is that this is the donor level now in blue, and thus rather than electrons coming from all the way from valence band, even at a very small temperature like 100 Kelvin, this donors, which are, let's say in silicon this will be nitrogen or phosphorus impurities, they can donate their electrons, and the number of electrons can increase many folds. Similarly for acceptors, what we have is they have the energy level very close to the valence band given by EA, and now the electrons which are in valence band, rather than jumping all the way across the band gap, they can simply jump to this acceptor level. So this will be your typically the examples would be your boron or aluminium impurities in the silicon, let's say. So that's how we can increase the concentration of electrons or holes, and if the concentration is increased, now you can support more currents, which is what we want eventually. And also notice this kicks in, the accepting or donating of the electrons, whatever the case, this comes in only at certain temperature. We saw that below 100 Kelvin we experience something called a freeze out, because these donors or acceptors do not have even sufficient energy to cross this small energy gap from ED to EC or from EV to EA, whatever be the case. Finally, we saw the Ohm's law with J equal to sigma E as compared to V equal to IR, which I've been habitual of seeing. J is the energy current density, E is electric field, sigma we know the electrical conductivity. And we also saw that the drift phenomena, that is when you apply an external field, how the electrons will have a net motion, which is given by Vd equal to mu E. Mu is the mobility and V is the drift velocity, and this was given something like this. So this is Vd versus the applied electric field E. In the low field regime, the linear regime, this is the fashion, but if you apply sufficient high fields, the electron cannot electronic velocity cannot increase arbitrarily high, because it will now collide more with the lattice and it's lose its energy. And this we saw in the scattering mechanisms, the time between the two is called the scattering time. The other transport mechanism of charge carriers which we saw was the diffusion. Diffusion means concentration is high on one side and low on the other side. So due to the concentration gradient, the charge carriers, mobile charge carriers, will diffuse. And what we also saw is that this drift diffusion, the sense that if you have a semiconductor which is non-uniformly doped across its length, then it will have diffusion as well as drift. Ultimately an equilibrium will be achieved, and you will get d by mu equal to kt by q. This is the Einstein relation that we had talked about. Finally, the charge carrier density, the change in that is related to four phenomena: drift due to the electric field, diffusion due to the concentration gradient, generation, let's say you are shining some light predominantly, or recombination, if there is somehow this large number of electrons and holes in the proximity for given sufficient time, they can recombine also. So based on these four factors, the charge density depends. And finally, all the semiconductor physics we saw in terms of a p-n junction, which is nothing but a p-type semiconductor, n-type semiconductor forming a metallurgical junction. Holes will diffuse from p to n, electrons from n to p. What will form is a depletion region, which will look something like this. Depletion region means it's devoid of any mobile charge carriers. So on the p side there will be negative charge, because this is due to the acceptor ions, and on the n side there will be positively charged donors, because they have donated their electrons. This is a p-n junction. There are other flavors like pin. P plus n means p side is highly doped. Then we saw the p-n junction at equilibrium, which is the case in this case. We saw the charge profile, and you can see clearly that there will be electric field associated separation of charges, and consequently there will be electric field potential difference, which we called as VBI, the built-in potential, right? The depletion region, the width of it is called the depletion rate W. And when you go forward bias it, that means you apply p terminal, positive terminal of the battery to the p. So this barrier is lowered, and now the carriers can be injected, and the minority carriers will diffuse across the now shortened depletion length, and they'll recombine on the other side, and the circuit is complete. We saw the law of junctions in the sense that Np equal to Ni squared e to the power qva over kt. Va is the applied potential, the forward bias that you are applying. Then we also saw the reverse bias, and we saw that this device can break down. For instance, when you increase the reverse bias, it can so happen this depletion region widens quite a lot, and now you can simply apply your Newton's let's say third law, v square equal to u square plus 2as. This acceleration is being provided by the large electric field which is present here. If you have a large distance to travel, now the electrons can gain a large amount of kinetic energy. This kinetic energy can get so high that it can knock the, let's say this is the lattice ion, this electron can knock away this electron, and this cycle will continue, it'll rise exponentially. You will see an avalanche of electrons. In the reverse bias, you do not expect the current to flow, only the reverse saturation current to flow. That is not the case. A large amount of current flows due to the avalanche breakdown. Zener breakdown will saw in case of a heavily doped p-n junction. So in that case, the band diagram looks something like this. P and N side on a reverse junction, because it's rather P plus N plus, and thus you can see that you can have a current flowing, which is typically not the case, like this straddling that can take place. And a similar application was the tunnel diode, which you saw its characteristics, IB characteristics used to something like this. First, the current increases due to the band-to-band tunneling. Then the current reduces because the drift in the forward bias has not come into effect yet, and the tunneling has started to reduce. Finally, thereafter, the drift mechanism takes the drift and diffusion mechanism, the typical forward bias takes up. Then we saw the LED will come, photoelectric solar cell will come to the few, I think, next week and thereafter. Then we saw the second kind of junction called the metal semiconductor junction, also known as the Schottky diode. We talked about the two terms, work function and electron affinity. And these are two type of contacts, rectifying, non-rectifying. This is very important, because when you're saying that you are connecting the positive terminal of the battery to the P side, how is it even happening? This is happening because we are forming a kind of an ohmic contact which just transports the electrons on both sides, because it can be forward bias or reverse bias, the device that is. And those kinds of contacts were called the non-rectifying contacts, or also known as the ohmic in nature. That whether rectifying and non-rectifying depends on the work function and affinity of the metal and the semiconductor we are talking about. The mechanism here we talked about was thermionic. Then we saw increase the difficulty level a bit. Now we talked about three terminal devices called the NPN, BJTs, and the PNP. We talked about why the doping of emitter has to high, base has to be lowly doped, and its thickness has to be low enough. Collector is usually moderately doped and wide to decrease the to effectively dissipate the heat, that is. And we can see there are two junctions, base, so this is emitter, base, and collector. So base emitter and base collector, depending on the biasing of these two junctions, we can have the four different regimes, namely forward active, saturation, reverse active, and cutoff. Typically we talked about the working in the forward active mode, the various terms like emitter injection efficiency, that is, and the base transport. Base transport is essentially that how many electrons which are injected into the base from the emitter have managed to come to the collector. So typically, if you recall, in the forward bias, the band diagram used to look something like this. So this is your emitter, this is your base, this is collector. Base collector is reverse biased, emitter base is forward biased. So this is typically how it looked. Electrons get injected from here, very few recombine here, and most of them are collected over here on the collector side. And current gain is nothing but your beta, which is IC over IB. There are other terms which you can go through the lecture slides. Then we came to the very important device, in fact the building block of the MOSFET, which is a MOS cap. So we have a metal, we have an oxide, and based on a semiconductor. So this is metal, and this is a semiconductor which we usually ground. And then we saw its different types like P MOSFET and N MOSFET, and the four regimes we talked about: the flat band, the accumulation, depletion, and inversion. That depends on the so for a P type substrate, let's say if you do not apply any bias, that's a flat band condition. Accumulation, if you apply a negative bias, what you're going to attract the holes, so they'll accumulate at this oxide semiconductor junction. Depletion, you apply a positive bias, they'll get repelled and form depletion. And ultimately, a situation may come where the band bending can be so huge, right? The band bending can be so huge, and we saw that. So let's say this is the oxide, this is the metal side. We are applying a negative bias over here, and so we saw the band bending had become so huge. This is the Fermi level, let's say, right? And yeah, something like this. Sorry. So something like this. This is your EV, EC, and EF. If you look close in the bulk, EF is close to EV. That means it's predominantly p-type. However, at this interface, EC is closer to EF, that is predominantly n-type. So the nature of semiconductor from p-type in the bulk to n-type at the surface, this phenomenon is known as inversion, right? And there are various the voltage at which that happens, we called it the threshold voltage. It depends on the doping of the substrate naturally, and the metal choice, because that dictates the semiconductor work function, and the gate dielectric, it should be perfect and no trap charges and so on. And we saw the capacitance voltage characteristic also in both of high frequency and low frequency regime, if you recall, CV. So on the negative potential is the accumulation. So there it will be only equal to C ox. So this is your C oxide, epsilon ox by T ox. The oxide is here, right? And then you have depletion. So capacitance, now you'll have a capacitance of oxide in series with the capacitance of the depletion. So it will keep on reducing. And if you apply very high frequency, what goes to happen is that you're modulating this charge of depletion in the inversion layer actually, but that doesn't get sufficient time because the carriers have to come from the bulk to the surface. So what happens is that it remains flat. However, for a low frequency, this is for high frequency, for low frequency regime, you give sufficient time for the electrons in this case to form the inversion layer, to come and go as you modulate the voltage. So in that case, this is how it looked like for low frequency. Okay, we finally talked about non-idealities, like if there is a work function difference between metal and semiconductor and there are some trap oxide charges. Then last session we talked about MOSFET, its fabrication, the 4-terminal device. Essentially it's your it's source, drain, gate, and body. So essentially this is a MOS cap, but just you add, for instance, in the previous diagram itself I'm drawing, so just you add a source here and a drain here. Source and drain are n plus type both to form a channel which is channel of inversion layer, which is electrons, and the source and drain has to be n plus types. We compared this with a MOS cap and a BJT, that how in performance wise it's different. And we also saw that if we let's say if we change the drain voltage, just like we saw in case of a BJT, like IV characteristics, we saw the two regimes that it can happen. So we saw the output characteristic looks something like this. In the linear region, this is the linear region in which the channel is there, right? And it's still however, when a state will come which we call the saturation, where the channel has become pinched off. We analyze this using the gradual channel approximation. And finally, it's not that substrate here is usually it's grounded, source is definitely grounded, but sometimes you can choose this body terminal which is not grounded to just change the threshold voltage, because if you change the bias applied to this body, then effectively what it's in your control is threshold voltage, because now you can modulate the inversion layer from the bottom also rather than from the top, which is very crucial tool when a circuit is designed. Few terms that we had talked about in terms of performance were the on resistance, that is effectively the slope of this line in the linear region, the IV curve, that is transconductance denoted by GM. We had delta ID by delta VG. Conductance is current over voltage. Trans means output current over input voltage, and output conductance will simply, usually denoted by G0, will be del ID over del VD. We have in the session you can this early effect which you had seen in terms of BJT, counterpart of that. Okay, so that is that we had talked about in terms of the summary of it. Why I revised it, because we are going to invoke many of the principles like built-in potential, like band gap, and the Fermi levels, and all those concepts. In fact, different concepts from multiple lectures will be invoked, because this is now we are moving into a different regime of the devices, of the semiconductor devices, which are referred to as the compound semiconductors. Okay, so the first question is asked: which of the following are the examples of ternary compound 3-5 semiconductors? So it has semiconductors word we had talked about. So there are different terms. First is this term called compound. The second term is the ternary. I'll also come to 3-5. So that's an adjective again. So let's just first try to classify the semiconductor materials as of till now what we know. So if you recall, up until now, in fact not all, most of the discussion that we have had was based on elemental semiconductors and predominantly silicon. Elemental means there's only one element. So this is only silicon or this is only germanium, right? Then there's second category of these semiconductor materials called the compound semiconductors. So for instance, we had talked about a device when you're talking about LED called the gallium nitride, right? So just to be clear, so if you know group 4 elements, I'll just, this is group 3 and 5. So what we have is carbon, silicon, germanium, right? And then here you will have boron, aluminium, gallium, and so on. And on this side you will have nitrogen, phosphorus, arsenic, and so on. Okay, so elemental semiconductors, carbon is not a semiconductor. If you recall, it falls under the forgetting the term for that, which forms equivalent bonds, non-metal. So carbon is non-metal. Silicon, germanium are semiconductors. Aluminium and gallium are metals. So boron is also sometimes clubbed in the same category as silicon, but strictly speaking, group 4 elements are the what we're talking about, the elemental semiconductors. Okay, what you can do is you can combine one group 3 and group 5 element, and they'll expect them to behave like a group 4 element, which actually happens. So for instance, if you combine, let's say, aluminium and nitrogen from here, what you form is aluminum nitride, it's semiconductor. Gallium nitride is again a semiconductor, so I'm writing the example. These are called 3,5. Okay, 3,5. And finally, also another category you can have is of 2,6, group 2 and group 6. Okay, this is essentially based on the valency that they have. Otherwise, I think the group number here is 14th column in the periodic table, 15, 16. 18th is definitely your noble gases, helium, argon, and so on. So if I write it, this is oxygen, and then I believe sulfur, selenium, I'm not able to recall more examples of that, but 2,6, if I recall, is I think cadmium sulfide, one of them, or cadmium cyanide. I'm not able to recall right now, but one of them is what we call as a compound semiconductor. It behaves like a compound semiconductor. It behaves like a semiconductor, but it's made up of more than one element, hence the name compound. Okay, so so this is another example of that. Then there are other few, in fact, furthermore categories called, these are called transition metal dichalcogenides. So a very good example is MOS2. This is a semiconductor. In fact, depending, so these are usually in very thin layers. A single layer MOS2 will behave different than a 2-layer or a 4-layer or 8-layer. And these are usually, these we can exfoliate. I mean, we can grow or deposit only one layer, and try to find its properties, its electrical properties in this case particularly. Okay, so so this is again one of the how should I say, another class. So there are different compound semiconductors that exist, not just the flavor like only elemental. So that's one of the key differences: compound semiconductors and your elemental semiconductors. Compound semiconductors, you have further classifications: 3, 5, 2, 6, TMD, and so on, right? And the second term that I was talking about, so 3, 5, you now understand why compound is a separate category of 3, 5. In fact, 3, 5 also I can write is at gallium arsenide, again a very famous example. Okay, so you can see these are 3, 5. A subcategory of 3, 5 is called as 3 nitrides. As the name suggests, the first element will be from group 3, so let's say aluminium, and the second element has to be nitride. So here gallium phosphide will also be there. So 3 nitrides can be aluminium nitride and let's say gallium nitride. These have a separate field of their own, right? So that's why we classify them separate. The term here, the adjective that we have added in this problem was ternary. Ternary means 3. So for instance, these are unary, means only one element. The compounds, all the examples that I've listed on your screen till now are binary. So what can happen is, there's a ternary means 3. There will be 3 elements to it. So what it can mean is, as you can see, gallium nitride, aluminum nitride, they belong to the same family. What is the family? 3 nitrides. So what can do is, I can have, let's say, aluminium gallium nitride. Now you will see, okay, how will that exist, how will the valencies be satisfied. So more technical way of writing is something like this, where x will lie from 0 to 1. Now you can clearly see that this is the essentially the mole fraction. So aluminum mole fraction can lie elevate between 0 to 1, and you will transition from, if aluminum mole fraction is 0, what you will have is Al0 Ga1 minus 0. So that means you will have gallium nitride. On the other hand, if you have x equal to 1, you will have aluminum mole fraction as 1 and gallium as 0. So what you can do, and that's so what can happen is, it's cadmium selenide actually here. So this is not absolutely random. Okay, it's not like that you can combine any material with any other material. So MOS2 will not work well with, let's say, aluminum nitride. They have to be of similar family, because by family I mean their crystal structure is involved. Which is not going into that much detail, but essentially you can get an idea that if there are 3, 5, or let's say 3 nitrides, they are more or less compatible. All the arsenides, let's say gallium arsenide, aluminum arsenide, or indium arsenide, they are more or less compatible. So we grow it like that. By growing we mean the epitaxial growth. So all these materials which are listed here, they're grown into some machines which we known as the growth tools colloquially, and predominantly the two very basic examples. One is the MBE, molecular beam epitaxy, so, and the other is MOCVD, metal organic chemical vapor deposition. So these are the two reactors or the growth chambers in which we grow these devices, one layer over the other. This is not so straightforward. A whole lot of design as well as tuning goes into the first of all creation and then running of these devices. Okay, right. So mole fraction will determine what is it, but as a whole we can call it LGAN because it has 3 elements, a ternary semiconductor. It's a compound semiconductor. You can see it's more than 1 element. Ternary means it needs 3 elements and has to be 3, 5. This means all the species in this will either have to be from group 3 or group 5. Okay, so let's see, aluminium gallium arsenide. So aluminium is group 3, gallium is group 3, arsenide is group 5. So yes, this satisfies. It has 3 elements, it is a compound, and it has all the elements coming from group 3 or group 5, and it's a semiconductor also. Next is aluminium gallium nitride. So aluminium is group 3, gallium is group 3, nitride is group 5. So this is also satisfied. This is also semiconductor, ternary. Gallium arsenide, it's a semiconductor, correct? Is it a compound? Yes, it's a compound. Gallium arsenide made of 2 elements. Is it 3, 5? Yes, it's 3, 5 because gallium is group 3, arsenic is group 5, but it's not ternary, it's binary. So this is not correct. Okay, so it will have so in this case I can write that it will have only 2 options. But let's try to make some other elements 3, 5. Okay, ternary compound 3, 5 semiconductors. So one example that we know is indium aluminium nitride. This is again one, indium aluminium and nitride, right? Indium aluminium phosphide, indium aluminium phosphide, that's also accepted, right? You can just play around indium gallium arsenide, indium gallium and arsenide. So these are the different, and again you see I'm only talking about 3, 5 here. This is true for others, but 3, 5 have been most widely studied in terms of research, and there are some commercial applications for which the products are in the market. So that just lies down the very framework of the session that we're going to have today. We're going to talk about compound semiconductors, and they can be binary or they can be ternary. But please understand that not any material can be epitaxially grown over any other material. They have to belong to the same family. Okay, I'll keep on revisiting this concept of the family over and over again. Okay, I have said that you can have, let's say, ternary, or for that matter you can also have quaternary. These are also used in some applications. What do I mean by quaternary? So you can have indium gallium aluminium arsenide. This is a compound, and this is a semiconductor. It has semiconducting properties. it's a 3-5 because indium, gallium, aluminium belong to group 3 and arsenic belongs to group 5. So this is a ternary compound 3-5 semiconductor, sorry, quaternary compound 3-5 semiconductor. I mean, you can also say, okay, let's put 5 of them, but the growth of it and all, it has to be stable, it has to have some reasonable degree of, let's say, quality to this material, because these need to be crystalline in order to exhibit semiconductor properties. Remember that all of this discussion that we had in the Ronick binder model, it has to be periodic, it has to be lattice, right? It has to have a crystal structure. So those things, growth becomes more and more difficult if you increase the complexity in terms of, let's say, elements that we are talking. Okay. Now let's say we are talking about for this slide, let's say I'm talking about ternary semiconductors. Okay. Now how to determine their, let's say, different key physical quantities like the lattice constant, their effective mass, electron affinity, band gap, and so on. So how do we do that? So we do that, and please note that I'm talking in terms of ternary here or quaternary. So okay, so let's look at this diagram over here. So what we have is on the y-axis we have I'm only going to talk about the okay, so let me just take an example that would be better. Okay, so let's say again the example that I took in the previous slide, aluminium, gallium nitride. So this is a 3-5 semiconductor. I want to know what is the lattice constant for this particular compound. Okay, so I can write the lattice constant will be x times lattice constant of aluminium nitride plus 1 minus x lattice constant of gallium nitride. This is the lattice constant for this material. Let's call this, so I'm calling this L-GaN. The lattice constant for L-GaN, lattice constant is nothing when you have unit cells, the distance between, essentially the spacing between the two atoms, to put it very bluntly, because some people might not find it comfortable understanding lattice constant, is basically the distance between the two repeating units. So that for aluminum gallium nitride, for this compound semiconductor will be given something like this. Very, very simple. It's just whatever the mole fraction of aluminium is, you have it aluminum nitride. Mole fraction of gallium is 1 minus x. You have it like this. Very simple. Okay. Let's now try to raise the complexity a bit, and I'll write a quaternary one now. Okay. So indium x, aluminium y, gallium 1 minus x minus y nitride. So this time I have this quaternary 3-5 semiconductor. So let's try to write its lattice constant. So indium, aluminium, gallium nitride will have x mole fraction is of indium, so of indium nitride, so x times indium nitride plus y times aluminum nitride plus 1 minus x minus y of lattice constant of gallium nitride. A similar exercise you can do for effective mass and band gap. Band gap, it's a slight departure which we'll see in the next slide, but this is a fairly straightforward principle that you'll be able to appreciate. This is known as the Vegard's law. Okay, now let's try to see it for band gap, as I was saying, how it looks like. So what you have here is the essentially the lattice constant, of what they're calling the bond length in angstrom on the x-axis. You have the band gap energy on the y-axis. So as I was saying, focusing on aluminum gallium nitride family 3-5, so you have 3-5 or rather 3 nitrides over here, right? And as we have known that this orange circle denotes it's a direct band gap, which you can see here. Another semiconductor which we are seeing here is silicon carbide, which is an indirect band gap. So in this scale we are not able to see silicon is not plotted over here in this diagram, but you can see the 2-6 ones are over here, zinc sulfide, magnesium sulfide, and so on, right? And here are the phosphides, aluminum phosphide, gallium phosphide, some selenides, zinc selenide, cadmium selenide, indium phosphide, again phosphides. You can see different families of materials of semiconductors which are represented here. Okay, and now I just want you to focus. So for instance, now let's say we for a specific example, I want, let's say, mole fraction of aluminum, mole fraction of 25%. So let's say x equal to 25% or 0.25. right? So we know it will lie somewhere over here, the straight line joining gallium nitride and aluminum nitride. It will be somewhere along this line, correct? And the exact values of a gallium nitride, aluminum nitride, we do know of the lattice constant. You can get from this, and wherever you lie actually in this case, if x is 25%, so you lie somewhere over here, 1/4 the distance from aluminum nitride. So this is the point which will have Al 0.25, gallium 0.7. Oh, sorry, that's wrong. It will not be here, it will be closer to gallium nitride. So it will be somewhere over here. So this point will denote aluminum 0.25, gallium 0.75 nitride. Similarly, this point, if I mark here, it will be aluminum 0.75. I'm not marking it, I'm just saying. So this is how we can determine, and it will have a corresponding band gap energy. Okay, and this is a very a positive, very useful tool to have, to just have some first-hand estimates of various, where will the individual material of ternary semiconductor lie, because binary we are still able to study. Ternary, because we are growing them in the reactor, it's difficult to predict. So we difficult to know how it will behave, because it will have very non-idealities. So we must have first-hand, we must have an idea where it lies. Okay, right. So so in this question again, we are given an aluminum, gallium nitride and gallium nitride. So what happening is that, so essentially let me draw. So HEMT is nothing but a transistor. We have talked about transistors like bipolar junction transistor, field effect transistors. HEMT is just let's say a cousin of FETs. We need not worry about what it does is that, but the material is given here. So we have gallium nitride at the bottom. Okay, so we have a gallium nitride layer at the bottom, let's say, and on top of that we are growing AlGaN. So this is the AlGaN layer, and where it's 25% aluminum, so I can write it as AlGaN, rather I should say 25% AlGaN. So I'll write it like this. This is 25% AlGaN, right? And HEMT is nothing but you make source, drain, gate and whatnot, but this is the material stack, or we also call this the epitaxial stack. Okay, right. Calculate the band gap of this AlGaN barrier. So this layer, what they're calling this layer, they have given it a name called barrier. We need not worry about it why it's called barrier, but this layer has some. So aluminum gallium nitride, this layer is called barrier, and we are required to find the band gap of this specific 25% AlGaN barrier. Okay, and we are given the respective band gaps of aluminum nitride and gallium nitride. So in the previous slide, you see we had, in this diagram you can see all 3 nitrides, 3 phosphides and arsenides and 2,6 materials and whatnot. But this problem, first of all, I am ignoring the Boeing parameter. So what does that mean? As I told you, the band gap of AlGaN, if we apply Vegard's law to the band gap formulae, it will be something like this: X times Eg of aluminum nitride plus 1 minus X times Eg of gallium nitride minus a factor comes. Okay, this is called the Boeing parameter. What it's not given in the problem what it is, but it does exist. So for instance, what it means is that, so for the time being, let me just ignore this parameter. Let's say b equal to 0. So your Eg, the band gap for AlGaN, will be very similar to what we had seen in terms of the lattice constants. Okay, 1 second. Okay, right. So now let's just put all the terms here. So x value of x is 25%. So x is 0.25 times Eg of aluminum nitride, that is given as 6.2 plus 1 minus 0.25 times band gap of gallium nitride, that is 3.4 minus 0, because b is 0 and x is 0.25 into 1 minus 0.25. Okay, so we do this 6.2, 1/4 of 6.2 will be 1.55 plus 0.75 into 3.4, so that's 3.4 into 0.75, that is coming out to be 2.55. You add this 2 plus 1, 3.55 is, so this will be 4.1 EV. So the answer is 4.1 EV. Okay, and so if I write the band gap, if I denote the band gaps here, so this has band gap of 3.4 EV, this has band gap of 4.1 EV. What you're forming here, you're combining two different materials in close proximity. This is very similar to what we had, like the p-n junction we had talked about, two semiconductors forming a junction, right? Similar thing is happening here. I mean, there are other complexities, but fundamentally two semiconductors are in close proximity, they are touching each other. But this is called as a heterojunction. Why heterojunction? Because these two materials have different band gaps. The p-n silicon, if you recall the, let's say, the p-n junction, your p-n junction silicon, right? In that both sides are silicon. This is known as a homojunction. Homo means same, junction means two different semiconductors are coming together. This on 25% L-GaN to GaN is a heterojunction. Okay, they might have doping and whatnot, but due to the fact that there are two different semiconductors with different band gaps forming a junction, this itself is known as a heterojunction. So this is an important definition which I suggest you remember, because this is a very fundamental when you make devices out of these compound semiconductors. Heterojunction devices are one of the most famous ones. Okay, right. So I was saying to ignore this Boeing parameter. Now we have obtained the answer, that's fine, but let's just try to explore a bit what happens if we do not ignore this Boeing parameter. This Boeing parameter will be a positive quantity. Okay, so let me just draw this, how it will actually look like. So this is your band gap, y-axis is Eg, x-axis is let's say mole fraction of aluminum, which we are denoting as x in this problem. This is increasing, so over here is x equal to 0, let's say here is x equal to 0.5 and here is x equal to 1. So when x equal to 0, this means we are talking about if x equal to 0, we are talking about gallium nitride. Okay, so let's plot this. So gallium nitride, what will x equal to 0 means gallium nitride. So gallium nitride band gap is 3.4. So let's say this value is 3.4 and we obtain this point. Okay, at mole fraction of 0, this L-GaN will have the band gap of 3.4. And let's say when the mole fraction is 1, we'll get aluminum nitride. So we'll get aluminum nitride means band gap of 6.2. Let's say this is 6.2. We'll get this point. If I ignore the Boeing parameter, what you expect to get is this straight line. And let's say when mole fraction is 0.5, you must get the so we had done also 0.25, right? So 0.25 we had obtained 4.1. This point we had obtained 4.1. For 0.5 you should get exactly midpoint, which is 4.8, and so on. So you'll get this on a straight line if you ignore the Boeing parameter. However, in practice, what we have noticed is that this is not a straight line. Experimentally observed, this we do not follow a straight line, rather it has a certain bow to it. So for straight line says you must get, let's say straight line says that you must get, I'm showing in purple, you must get this value. What you actually observe is this. So observation, this is the observed value and this is the theoretical value. So observed value is slightly smaller than theoretical. Now we have to change this expression to accommodate for that. Okay, hence this Boeing parameter comes into the picture. So this question can be asked in different ways. So for instance, so Boeing parameter, so the question can be asked, a Boeing parameter in Vegard's law does which of the following? Option 1, let's say it depicts the departure from the linear behavior, which is true. It depicts a departure. So, and the second can be, let's say, Boeing parameter exaggerates the band gap for the compound semiconductor. Option 3, Boeing parameter decreases the estimate of the band gap from the straight line. So you can see it decreases that. So there are different ways in which Boeing parameters problem can be asked, especially in competitive exams. So that was my idea, just to highlight this point explicitly, that Boeing parameter is important. We for lattice constant we don't bother it. Only in the band gap this is a primary concern, and it can vary. So for instance, you see that the bow will be somewhere highest between 0.5 and 0.6. So when you are mixing materials, when the growers who are growing in the reactor and they say that, oh, we were expecting 4.8 EV of band gap for this particular material, but we are getting only 4.5 or 4.1, what is the problem? So that's how it was observed, and that's why this expression was corrected to account for this difference between theoretical and the observed values. Okay. Now, as I was saying that these layers are grown on top of each other, which in this slide you can see I talked about gallium nitride, and just above that you see 25% algan. So how is that happening? Essentially, these are some chemical reactions that are happening. So when you're growing gallium nitride, you open the valve, just allowing the precursor for gallium and precursor for nitrogen. When you want to grow algan, you open also the valve for aluminum. Now the flows have to be carefully monitored in order to achieve this, let's say, ratio of 25%. So that's where the hard work and the optimization lies actually. Okay, so yeah, so I was saying in the epitaxial growth of compound semiconductors, as I have been saying. So let's take the example. So this is a different picture, but in this case I'm only showing the 3 nitride families. So you can see gallium nitride, aluminum nitride, and indium nitride. Silicon is also reflected here, but I'm only showing these 3 let's say binary compound semiconductors, and in the middle you can also see this algan. So you see on this blue line algan will lie. On the red line, what you can see is the alloy of gallium nitride and indium nitride. So it will have expression of INX Ga1 minus X nitride. On the green line, on the other hand, you have indium aluminum nitride. So aluminum nitride and indium nitride, and you can see this will like something like this. And you can also see it's not a straight line. It's a bow is associated with that. So this bow is coming because on my axis we have the band gap. So it's not a straight line. It's rather it's most clearly seen in terms of indium gallium nitride. You can see there is a significant bow to this. Okay, that's coming essentially from the Boeing parameter of the Vegard's law in context of the band gap. Okay, so what I was saying is that let's say you are growing gallium nitride. So I'll try to show it in a way. Just a second. So let's say this is the first layer of gallium nitride you have grown. Gallium nitride is in red color, and then above that you are again growing the second layer. These layers I'm showing it explicitly, but these are very thin, barely a few nanometers. Layer 3, layer 4, and so on and so forth. Let's say you have grown 100 layers. Okay, so all of this, let's say it's layer 100. This is all gallium nitride. On top of it, you want to, since aluminum gallium nitride is of the same family, okay, you can grow it. Okay, so let's try to grow it, denoting in blue color here. So you will have layer 1 of it, and let's say I'm growing only 10 layers of this. Why 10 layers? That depends on the application that we have, but let's say I'm growing only 10 layers of this. And for the sake of discussion, let's say that each layer is 1 nanometer thick. So this is your algan, and let's say 25% only. So Ga 0.75 N. So each so this is how it's going to look like. Let me be more aggressive here, and let's say these are 1000 layers of gallium nitride. Okay, 1000 layer of gallium nitride and 10 layers of, let's say, aluminum gallium nitride. So total thickness would become 1000 nanometers or 1 microns of gallium nitride, and let's say for the LGAN it will be 10 nanometers. Each layer, each rectangle is 1 nanometer height. Okay, so as I told you, how do you do it? You just turn on a valve, aluminum will start to flow, and let's say you know the magic and how to form exactly this compound. What I'm more interested in showing is how at an atomic level how it looks like. So I need you to pay attention to the lattice constant. So let's say the gallium nitride lattice constant is 3.2. As you can see from this diagram, it's approximately 3.2. So let me try to draw this. How will the gallium nitride, I'm only drawing, let's say, the 1000, let's say this is the, so at the very bottom, we have the layer 1. This is layer 1, layer 2, and finally what we have is let me show you. I have to be very clear with this, otherwise it may cause some confusion. So this is layer 2 of gallium nitride, and finally we continue and we get to, this will be a crystalline structure. So this is layer 999 and this is layer, this is the direction of growth in this direction. This is layer 1000. Now on top of this I want to grow, so this distance is 3.2 angstroms, right? And let's say if we see the lattice constant of aluminum nitride, it's 3.1, and if you calculate it from your Vegard's law, you can clearly see that this will be somewhat smaller than 3.2 angstrom. Okay, right? So let's say that lattice constant is so for I'm growing LGAN on top of it, right? So that lattice constant will be, let's say, 3.1. For the sake of discussion, let's say its lattice constant will be 3.1. Okay, in blue color. So 3.1. So what's going to happen is it will grow something like this, slightly smaller, right? I'm showing only 5 dots just to denote the 5 cells here. So what you can see that, but it has to grow directly above this. So this point, now I'm showing in a different color to demonstrate what I mean to say. This point has to be fixed to this. This has to be fixed to this. This has to be fixed to this. This to this. This to this. So what you're forcing is that even though it wants to be of a smaller length, what you're essentially doing is you're stretching it. Each of them, rather than being 3.1 or whatever, let's say 3.1 its length, you are forcing it to be 3.2. What it means is that this layer of LGAN is stressed. It's not relaxed, it's stressed. You're forcing it to be something which it does not want to be. It naturally wants to be at, let's say, 3.1 angstroms. You're forcing it to, because you've grown it over gallium nitride, you're forcing it to be 3.2 angstrom. The distance between two atoms or two cells, you're forcing to be 3.2 angstrom. It does not want that. This means LGAN is stressed here. How stressed? There are two types, compressive or tensile. What you are forcing it to? You're forcing it to stretch. What kind of stress? This is called the tensile stress. You're forcing. Where does stress come from? Because you are growing on gallium nitride. That's where this tensile stress comes into the picture. Okay. On the other hand, let's say you are growing. Okay, I'll take a rather. I hope I am able to point out here. Okay. So let's say what you want to do is you want to grow. So on the gallium nitride bottom layer, you want to, rather than growing aluminum gallium nitride, you want to now grow indium aluminum nitride. So that's why how we write this, indium aluminum nitride / GAN. So this is the top layer, this is the bottom layer. So GAN will have somewhere over here, right? However, if you and indium aluminum nitride will be somewhere along the green line, correct? Look at this point, which is directly above the GAN. This point is directly above the GAN lattice constant. This means if I take such value of y, okay, if I take such a value of y such that this lattice constant matches exactly that of GAN, and that value actually comes out to be 0.7. So if I have indium 0.17, aluminium 0.83, nitride, GAN, this will have no stress. Why? Because it's lattice constant. So this is the point that I'm drawing here. This point will have exactly the same lattice constant as gallium nitride. This we call as the unstressed or the lattice matched. The more commonly used term is lattice matched. So in this case, 17% indium aluminum nitride will be lattice matched to gallium nitride, and you will not have this tensile or compressive stress coming into the picture. But this is the thing that we have to live with, and also lies in this the same answer that, for instance, you cannot grow, for instance, let's say the lattice constant for gallium arsenide. Gallium arsenide lattice constant, it's somewhere around 2.45, let's say 2.5 angstroms, okay? And you want to grow, let's say on gallium nitride, you want to grow gallium arsenide. Gallium nitride lattice constant is 3.2 or thereabouts. You can't grow a compound which has a lattice constant, okay, which is much higher. This is the chemical bond length is a different thing, but essentially its lattice constant will be higher. So which are widely apart. So here they are fairly close. You can see this is all lying between for instance 3.1 to 3.6, and they're of the same family, right? You cannot mix and match materials based on your bill. They have to be of the similar family. So 3 nitrides can be, yes, they can be grown epitaxially of a decent quality. If you don't grow that, the stress will become too high, and either they'll not grow or the films will crack essentially, which is of no use. It will be so defective. Okay, so these are the things that we need, that the growers need to keep into account for a good quality of epitaxy, and only on a good quality material, good quality device will be made. That's a separate story. Okay, so now coming to this problem, the pseudomorphic layer of 25% L-GaN grown epitaxially on GaN R. So let's visit this. So we had discussed this problem itself in the last slide. So gallium nitride is somewhere over here, but your growing is L-GaN, right? So L-GaN will have lower lattice constant definitely than GaN. So I can write will have lower lattice constant than underlying GaN layer. What does this mean? This means L-GaN will be stressed tensile, because there will be a stretching effect to the L-GaN, right? So it is tensile strength. Now there is a word that is being used here, the pseudomorphic layer. The pseudomorphic essentially inherently, so morph means shape. Pseudo means you are changing the natural shape of L-GaN. Why it's changing? Because they're growing on GaN. So that's why this term pseudomorphic, essentially in this context it means that. Okay, pseudomorphic nature of L-GaN means that, because it is under stress. Okay, and in this problem it happens to be under tensile stress. However, let's say, or a second problem, you are growing the bottom layer of gallium nitride. On top of that, let's say you are growing indium gallium nitride. So you can see that will have a higher lattice constant. Indium gallium nitride will have a higher lattice constant than GaN. So what will happen is that the GaN will try to squeeze it in order to bring it to its own lattice constant, and then in that case this in-GaN layer will be compressively stressed on GaN. Okay, so it's always important to state which layer is the top layer and on which layer it is being grown. Then only you can make a comparison of the stress, because essentially you are comparing the lattice constants of these different layers. Okay, please keep that into account. This is of vital importance when we are going to analyze these layers, these epitaxial stacks or epitaxial layers of different materials that we are growing. Stress is a very vital entity, especially in three nitrides, because these are also these are piezoelectric effects also. Okay, so these materials, if you recall, piezoelectric materials which have, if stressed, they have a different kind of electrical properties. They exhibit enhanced or reduced electrical properties. Okay, so that plays a very important role, in fact, in the device which you had seen in question 2, called the HEMTs, the high electron mobility transistors. This effect is particularly used, the stress of the upper layer, and like for in this case gallium nitride layer, this how much stress you want it to be, this is of primary importance. Okay, so that is about this problem. Now we'll move forward um, to a problem which I had we had this LED. If you recall, this problem LED, this has been coming in our discussion over and over again. This is not the first time that we have encountered a problem related to LED. In context of PN junctions, we saw it, and then in one more application we had seen it. In the next lecture, we'll have a full-fledged discussion on it. But for just a second. I'll discuss this question which I posted in the comment in a bit. Okay, I'll discuss this. Just hold on a second. Right. So here we have the question says that a quantum well LED needs to be made of a heterojunction. So heterojunction we have talked about, in which the two materials of different band gaps form a junction. Remember that for good light extraction, the portion of semiconductor stack where light is emitted must have different band gap from the surrounding material. So essentially this is some stack we are growing. Okay, so and in that consider the material in which light is emitted GaN. So we have to base a GaN based LED. So what this means essentially is that there is a layer GaN, right? This is where the primary light will be, the photons will be coming from this layer. Okay, which of the can be surrounding material? So there is some material surrounding it. Okay, let's call this material X. We don't know what this material is, so it is surrounding, and again please recall, this is the direction of growth. Okay, so let's read this problem again. Quantum well LED, so we need to make a device LED from this of a heterojunction. You can see this is a heterojunction, so there's some semiconductor X and gallium nitride. So this X cannot be gallium nitride, and which is also not in either of the options, so we are good there. For good light intersection, portion of semiconductor stack where light is emitted must have different band gap from the surrounding material. Hence this is a heterojunction. This is gallium nitride, this is some other material of different band gap. Thus we have in fact two heterojunctions in this problem, just like a BJT where we had two PN junctions. In this problem we have two heterojunctions. The light material where light is emitted is gallium nitride. We have already written that. Which of these materials can be used as the surrounding material so that the light extraction is good? Assuming that the materials given in the options can be grown pseudomorphically. So again the same term, essentially you are growing them, they are strained, but they're not so strained that they break. Okay, the shape has changed slightly, but still they retain their more or less, the defects have not increased so much. So that's why this clarifies that we are growing them in a defect-free fashion. Essentially, your growth is perfect. That's what this problem in the last line suggests. Assuming this assumption, what is written here says that assume that the growth is perfect. Okay, so we have to grow this stack now. Sorry. So what we want is that we want the material. How do we want the material to look like? That's how. This is the material X. That's what we want to. Okay, so in order to understand how the efficient design of an LED looks, let's first look at a typical homojunction LED. PN, it has to be a PN junction. So this is on the left is P, on the right is N. This is a homojunction, so this means on the left and right they have the same material, and let's say this is gallium nitride on both sides, p-GaN and n-GaN. Okay, this is no bias because EF is constant. Rest of the things you can see. So red is your electrons, blue is your holes. Let's put it under forward bias. Again, the homojunction, you can see the band gap is same on p side as well as the n side. This is the same. Okay, so how it will look like? So electrons will start to flow, and on the other hand you can say the holes will start to flow from left to right. And what can happen is that the electrons are on the p side, they can recombine with the hole which is present here, and thus in this process emit a photon. Similarly, the same thing can happen over here in this, and these lens are the diffusion lens. So only in these lens you'll have this emission happening of a photon. Okay, the emission can also happen from the right side. The electron which is there can simply recombine with the hole. All right, this is under forward bias. Now, but you can see a problem. So whatever the photon is being emitted here, it can again be reabsorbed by this electron, let's say, and this will cause this electron, I'll show in a different color. If this photon is absorbed by this electron, this can again go here. So you will not have a photon coming out, so this photon has been absorbed. This is an inefficient design. Even though the photons are being generated due to the recombination, these two photons, but these photons can be reabsorbed. We do not want that, and hence the requirement that this photon is being emitted is not reabsorbed. We have to ensure that. How do we do that? This is a typical the quantum well design which the problem suggests. So what you have here is that you can first see that this material X that I was talking about. Just a second. So this material is some unknown material X. On this side also same material X. This is a gallium nitride in the middle. So what you see is that an electron and hole will recombine, something like this. A photon will be emitted corresponding to this wave, this band gap. So let's say this band gap, we know it's 3.4 eV for gallium nitride. Now this photon is useless because this band gap you can see on the right side or on the left side is much larger than 3.4 eV. So this 3.4 eV photon will not be absorbed either on the left or on the right. This is a much better design than the homojunction design. This is the heterojunction. Again we are applying the forward bias, and here you are also effectively containing the electrons, so they just don't go traveling outside this well. So essentially trapping them, you are allowing them more time so as to recombine. So that's a much efficient design. This is a quantum well design for an LED. There are different flavors of LEDs, quantum well inspired LEDs. Okay, so the photons essentially will not be reabsorbed. So first thing we notice that this mysterious material X must have a band gap larger than, so this is the summary for that. We have the homojunctions in the A and B, right? In the heterojunction you can confine them in this quantum well, right? They do not diffuse over this diffusion lens, right? Okay, so what we have noticed is that first thing, this mysterious material X, so this is essentially, so you can see the growth of direction is this is the growth of direction of growth rather, which I have denoted something like this, X GaN and then X again. This was the direction of growth. So first thing we clearly notice is that the X has to have a band gap larger than band gap of GaN, right? This is gallium nitride, so we can see that Eg of X must be greater than Eg of GaN. This is the first thing. Second, it must be of the same family as GaN, or let's say same family, that means 3 nitrides. So this mysterious material X has to satisfy these two properties. Let's look at the options. So one second, yeah. So if you look at, this is the different materials that we know, like 3 nitrides, indium nitride and aluminum nitride. So all of these 4 options satisfy that they are the family of 3 nitrides. Now But what we want to know, or what we need, is that this material X must have a wider band gap than gallium nitride. So indium nitride has a lower band gap. You can see it's much lower than 3.4, which is the band gap of gallium nitride. So this option is eliminated. Algan. So second option that is being suggested is you make this material as algan. So this means you are somewhere on this blue line, or in fact you are over here, right? So if you are over here, what you can do is okay, so if you are at this point, what you have the band gap which is larger than your gallium nitride. So this is an acceptable option, right? Second option is the indium gallium nitride 17%, which I told you will lie somewhere over here, this, because this is also lattice mass, and this is actually one of the best ways, because now it will not even be tensile stress. Again, that depends on your application, but if you don't want it tensile or compressively stressed, this is one of the best options. So yeah, it lies exactly above this. We know this from experiments. It's 17% indium aluminum nitride lies directly, is lattice mass to gallium nitride. So this also is an acceptable option. The third is aluminum nitride, which you see over here. This is definitely acceptable. So these three options, these satisfy all the two conditions that we had. The band gap has to be larger than the gallium nitride, and it must be of the same family as 3 nitrides. So this is these are the correct options. If I had to choose, that I have to choose exactly one, I would have chosen actually indium aluminum nitride. Indium, oh wait, the second option is not indium aluminum nitride, it's indium gallium nitride. So indium gallium nitride will lie somewhere on the red line, which has band gap lower than 3.4 eV. So this option is actually incorrect. Sorry about this, I misread it. So I'll write where each option lies. Okay, so option 1 lies here, option 2 is 17%, so option 2 will lie, let's say, somewhere over here. This is, let's say, option 2, and option 3 is aluminum nitride, so this is option 3. So band gap has to be larger than gallium nitride, so option 1 and 3 are the only correct ones. So 1 and 3. Okay, right. So a problem which is these kind of problems do come up for researchers, and sometimes industry and sometimes other actors approach the researchers to find such a material, grow such a material, find out what is the best we can do. So this is such kind of problem that in this question, let's say company at Bell Labs, their scientists have fabricated a device such that there is selectively drift mechanism of only electrons. How did they do it? That's the question. So let's say p-n junction of silicon material. So in fact all the three are p-n junctions, just the material has changed. So how does a p-n junction look like? We know it looks something like this. This is p side, this is n side. I'm drawing in what do you call, in equilibrium. Okay, so this is your EC, EV. You have a depletion layer. So option 1, 2 and 3, in all these three cases, the structure will look something like this. That is happening because the band gap has to stay the same, whether it's silicon. So silicon will, this is a homojunction essentially. All these three, in the first three options, these are homojunctions, because the material on the left, p material as well as n materials, belong to the same band gap. Silicon in first option, germanium in second, gallium nitride in third. It doesn't matter, the band gap across the whole length of the device will remain the same. So if the electron, so for instance, where does the drift mechanism comes to the picture? Drift mechanism, if you recall, if you see the electric field is nothing but the slope of so for instance, electric field for electrons will be, I'm just writing the magnitude. Okay, this is something like this, the slope of the conduction band for electrons, and for let's say for electrons, electric field for holes will be del EV over del X. I'm just writing the magnitude. The directions obviously we can determine how they're going to travel. So the slope, because the band gap in homojunctions will remain the same, that is the distance between EC and EV will always the same. Whatever slope will the EC will have, EV will also have. So electron and holes will experience drift at the same time, at the same position in time, I mean, okay, the same position. So the drift of electrons cannot be decoupled from drift of holes for a homojunction. Is it possible in heterojunction? Let's see that. So what we are doing is heterostructure junction using grading. So what do we mean by that? So let's say that so this is my first, I'll use a different color for this. Okay, so let's just say I'm using some material which has this much band gap, and then I use another material which has this much band gap. I'm just showing the slices. So let's say each of the slice of the growth step is, again, let's say 1 nanometer or something. Okay, then again valence band is somehow I'm maintaining that valence band, conduction band energy increases. So essentially what you are seeing is that the valence band energy remains fixed, but the conduction band energy is gradually increasing. I'm just showing very small steps to illustrate my point as to how is that happening. I'll tell you in a minute, but let's just see that how will the overall picture in this case will look like. So each step you're increasing the conduction band and valence band gap. That is, you're increasing the band gap of this material such that somehow you're maintaining that your valence band remains flat. So that is again a challenge in itself. Okay, so I've drawn enough now. So let me just draw this now macroscopically, how it will look like. It will look something like this. This will remain flat, which I'm drawing in black color, and this will look something like this. Okay, so what will be the electric field for electrons here? It will be del EC over del X. You can see some slope is there, right? And what will be the electric field for holes? This will be del EV over del X. This is flat, this will be 0. What's going to happen in this device, in the second case that we have seen, this is a heterojunction. In this heterojunction, only electrons will undergo drift, but not holes. So how will I choose the materials? First of all, again, please remember they have to be of the same family. So let's just go back to the, where is that diagram? This one, yeah, this diagram, let's say. Okay, so which family do I choose? Gallium arsenide and aluminum arsenide. So you see their band gap is let's say more or less similar. So I mean they can be grown on top of each other, and so energy of gallium arsenide is smaller, aluminum arsenide is larger. Okay, so what I mean here is that this edge is, let's say, perfect gallium arsenide, and on this side we have aluminum arsenide. In the middle, however, we have gallium X, sorry, I should write it the other way. In the middle, however, we have aluminium X, gallium 1 minus X arsenide, and X is increasing in this direction. Okay, so here the band gap, you can see, continuously keeps on increasing, and we have to obviously ensure that we have to choose such a family. This is the trick, and how we choose we'll come to when we talk about the band structures, but this is at least imaginable. If not practical, you can appreciate that this is possible. You just have to figure out a way to ensure that the EV remains the flat for all these different compositions. Okay, this thing is also known as grading when you're changing the X. Grading is nothing but change in X. So this X change in X can be exponential, can be linear, it depends. So for instance, in the quantum well that we saw, in the HEMT aluminum gallium nitride that we saw, it was an abrupt step change, only one change, right? But in this case we are seeing it's gradually increasing, so it can be linear or exponential, let's say. So such a device is possible, that where only electrons drift. This is using, for the example, the gallium arsenide to aluminum arsenide linear grading, let's say, using that kind of heterostructure. So each of these, the colors that you see, is a heterostructure. So violet and blue is heterostructure, dark blue and sky blue another heterostructure, sky blue to green, green to light green to yellow. All these are different heterostructures. It's just that when you see at the macroscopic picture, they look like a continuum. Okay, and this is possible only where the growth is of good quality. Otherwise, it will be a horrible device. Right? Okay. So next, again, a requirement. These are some requirements do come from industry or from government sector. In this case, it's like scientists from ISRO want to fabricate a switch for DC to DC conversion. So this DC to DC conversion is we do typically encounter. So for instance, you want let's say your battery is storing at 5 volts, but your battery is storing, let's say, 50 volts or 220 volts, and you want to use it for an application that uses only 5 volts. What do? You step down from 220 volts to, let's say, 5 volts. You want to step up. That's a DC to DC conversion. Electric vehicles do use this DC to DC conversion. And we also require a speed, that how fast you can switch from on to off and off to on. And that depends essentially, the switching speed depends essentially, among other things, on mobility. So in this case, we want a DC to DC conversion, which a mobility of 7,000 to 8,000 centimeters square per volt second. Now, this is a problem that is, there's not much to tell you from this. It's just that these 4 devices that we are seeing here. So this is your graphene. This is typically your 2D. Excuse me, just a second. Yeah, so what we have is graphene is a 2D material. MOS2 I also talked about in the introductory slide, where I was talking about the different compound semiconductors. Their mobilities are very low, like tens of, if it's code, maybe hundreds of centimeters square per volt second. So these are they have their applications, but not for this application, the one which you're targeting. These two, what we can have is some strain. Again, the strained silicon, you can strain this silicon to enhance its mobility in the mobility. So electron mobilities or hole mobilities can be enhanced. So in this case, their mobilities do rise to a few thousands of centimeters square per volt second, but still not as high as the one which requires. A gallium arsenide heterostructure can easily provide us this mobility of 7 to 8,000 centimeters square per volt second. This I'm not giving any argument as to why is it. There are complex reasons behind it, but just by from your perspective, you want to understand the idea of this problem was just to tell you that different applications require different materials. That's the whole idea of this. Okay, so for this application, gallium arsenide does suit our need because it has the higher mobility that we require. For certain applications, gallium arsenide is not required, is not suitable rather. Certain applications, there is another compound semiconductor called gallium oxide, Ga2O3. It's a 3,6. Gallium is group 3, oxygen is group 6, so it's a 3,6 compound semiconductor that is used for your power applications. Okay, so but its mobility is not that promising. So again, there are trade-offs involved in this. So for this works fine for us, and we go with this. Okay, now till now I've been talking about that. Okay, you can grow, let's say, to a reasonable degree of satisfaction. You can grow one layer over top of the other if they are of the same family, and they have their band structures. They have their band diagrams, their different band gaps. But I have never drawn a band diagram where two different materials of different band gaps are joined together, like we did in PN junction. Remember, we formed a metallurgical junction, then we say okay, there will be a diffusion of holes and whatnot. Okay, we'll come to the depletions regions in a bit, but first let's try to understand what do I mean when we have band alignment, so to speak. Okay, so first we have is something called, what I'm going to draw here is the vacuum level. This is we had also talked about this vacuum level, if you recall, in the when we are talking about Schottky junctions, right? The vacuum level. And let's say now I'm drawing the first the material. Let's say this is the EC. Okay, this is the EV, and we know this is the electron affinity, so let's call this chi1. Again, this is all one on the left side. Okay, and let's just say, for the sake of discussion, I'm not drawing EF, the Fermi level, as of yet. I'll assume that all the Fermi levels are aligned for now. For this discussion, I'm saying they are aligned. Okay, so let's say this is the I should not have drawn this dotted. Just a second, sorry about this. Okay, let me draw the second material first. So let's say the second material, it can be anywhere, so it essentially depends on chi2, because remember, vacuum level is the one that is fixed, that is the reference that we have taken, right? And based on only the reference, we can draw the second material's band diagram. Band diagram. So let's say this is chi2, electron affinity for material 2. This is EC2, and I don't know, maybe here lies EV2. Okay, and again, the assumption here is that, which is a very strong assumption that I'm making, which is almost never the case. This is the Fermi level. Okay, so this is what I'm doing now. I am going to bring them together. Okay, so actually I should do it like this, in fact. EF2 and EF1. So these are two different materials. The junction has not been formed yet. Okay, and again, as I'm telling you, where the value of EC1 and EC2 lie, obviously the first should have been more clear. Second, it looks like they have the same band gap. Let me just correct this. So this is EC2, sorry, EV2. This will be EV2, valence band, and for the other structure, let's say this is EV1. Okay, so you can now clearly see these are two different materials. They have considerable difference between the band gaps, and the electron affinities are slightly somewhat different. When we join them, so we can, depending on the value of chi2, it can have different flavors. So these are the three different flavors that you can achieve. So again, the structure that I have drawn, when you form a junction, these are the three things that can happen. So if it just so happens that the material 2, the lower band gap material, lies perfectly in between the conduction valence band of the higher band gap material, this is what's called straddling. Straddling means fitting inside. So you can see the second material fits very nicely inside the band gap of the first material. And this is the example that we had seen in terms of, if you recall, the GaN LED example, right? It was just like this. This was the first material, second material, third material was again the first material itself. Okay, this is the first material, this is the second material, here again first and second. Okay, that depends on the value of E. So this is a perfect, the diagram that I have drawn here fits very nicely with this. This, when you join this will look something like this. Okay, let's extend the discussion now to add let's talk about the other two as to at least how they look like. So again, the left one I'm not touching. The left one, let's leave it as it is. EC1 and EC2. I should draw some lines. Okay, so I've seen EC1 and EC2, and now let's draw the, this is EV1, this is EC2, this is somewhere EV2. Okay, this again is your chi1 and chi2. So the primary difference that you're seeing over here is just that the band gap are much closer in this case. It's just that the chi's are different, right? Chi's are definitely different. You can see the this is EC2, this is rather EC. If you combine them, it will, for the whole device, you will form the conduction band and the valence band, just like we have in the PN junction, right? So here you can see that the chi2 is definitely higher, and their band gaps are still more or less comparable. It's just that their electron affinities are different. Band gaps are definitely different. You have to trust me on this. They look similar, but they are different. The electron affinities are different, and hence you can see this type of a behavior, like a staircase type of a behavior, also known as type 2 or a staggered gap. Okay, again here this EG1 is greater than EG2. The right one is smaller. Okay. A third case which is even more extreme is, now you can see, so here chi1, chi2 was slightly larger than chi1. You then increase chi2 much further, and then in the third case, EC1, EV1, it remains the same. This is chi1. This is even more aggressive. In fact, such aggressive, chi2 lies even beyond the valence band level of the left semiconductor. And this is your EC2, this is your EV2. So if you form a junction in this case 3 or type 3, you'll get something like this. This is called a broken gap. You can see that, I mean, the valence band, the conduction band, valence band are essentially aligning here, but there will be some depletion and some other factors will come with the picture which will not give it such a the realistic picture will look somewhat different from this as it's seen here. Okay, so these are the three different ways in which these can be arranged, right? And right now we are not coming into the complexities of doping, because if you add doping, EF1 and EF2 will also start playing a role. We'll come to that, the doping and how, or if at all they play a role. But first, let's just try to solve a couple of problems just based on understanding of the three types of the band gaps that we have seen. Okay, so here we have in this problem a heterojunction formed by undoped 0.5 L GaN and GaN, and we have to calculate the total band discontinuity. Okay, and obviously we'll obey the Vegard's law. So for instance, the band gap, so first we need to find the band gap for this fellow and also the electron affinity. So we need to know two things, but first let's just call so EG1 that is of L GaN will be 0.5 times band gap of aluminum nitride plus 0.5 times band gap of gallium nitride, and I'm ignoring the Boeing parameter again. So this will be 0.5 times aluminum nitride is 6.2, 0.5 times 3.4, so this is 3.1 plus 1.7, this will come out to be 4.8 EV. So left is 4.8 and this is 3.4, and next thing we need to know is the what we require to know. So first of all, I am ignoring the band bending, or the, if the Fermi levels are not the same at the both semiconductors, some electrons or holes will drift from one side to the other, which will give rise to the depletion region. Okay, I am ignoring that for this problem. So but that is always the realistic picture. Okay, so next we need to find so first of all, you can clearly see there is a very simple way of saying that the total band discontinuity That is straightforward. It will just simply the difference between the two, difference between the band gaps of two semiconductors. So in this case, it will be 4.8 EV minus 3.4 EV. That's 1.4 EV. Where do these discontinuities lie? That's what we'll talk about. Okay. For that, we let's first just try to see what are their electron affinities. So for that, I have a sheet open. In this, electron affinity for aluminum nitride is 1.9, gallium nitride is 4.1. Okay, so let's do that. Let's draw our vacuum level. E vacuum. This is actually due to delta EC plus delta EV. This means jump on the conduction band and the jump in the valence band, which we'll try to determine what are they. Okay, so we have been given that electron affinity for aluminum nitride rather is 1.9. So again, I don't know anything. I'll simply apply the Vegard's law to get that electron affinity will be 3.0 EV. Okay, and its band gap is 4.8. This is ALGAN on the left side, please remember. So 3.0, so it will, so this will be your EC1, this is your EV1, and this band gap is EG1, which is equal to 4.8 EV. Okay, for gallium nitride side, we have been told that the band gap is 3.4 EV, and also the electron affinity is 4.1 EV. Okay, so let's draw first of all 4.1 EV. This will lie somewhere over here. So this is EC2 because the electron affinity is 4.1 EV. And just to be very clear, this side is ALGAN, left side is ALGAN, right side is GAN. Okay, and the band gap is 4.1 plus 3.4, so the bottom level will lie at 7.5. So this will lie somewhere over here, EV2. This is the band gap EG2 of 3.4 EV. What are these absolute values? If I write the absolute values, I'm doing in a different color, right? So this energy is 3 EV. This energy is 3 plus 4.8, that's 7.8 EV. This energy is 4.1 EV. I'm writing all this in reference to the vacuum level. And this energy is 4.1 plus 3.4, 7.5 EV. So you can see the left, the right material fits nicely, almost, actually it's very close. It's almost fits it's nicely into the band gap of the first semiconductor. And as we can talk about, this is the type 1 heterojunction, or the straddling. As you can see over here, this one, the first one, right? This is your ALGAN, this is your GAN. The GAN side, the lower band gap side, fits into the higher band gap side, which is shown over here. Again, I'm not drawing the Fermi levels or anything. Okay, now as I was saying, I have to draw the if I form the junction, actually, again assuming the Fermi levels are perfectly aligned before this, they will look something like this. Okay, so what will be the band bending here? This much. What is it? 1.1 EV. What will it be here? It will be 0.3 EV. So delta EC will be 1.1 EV. Delta E, so I can write that delta EC will be 1.1 EV. Delta EV will be 0.3 EV, and thus the total band discontinuity, delta E, which is naturally will be 1.4 EV, which we had determined earlier. So this is again a very big assumption, is that the Fermi levels, I'm assuming, perfectly aligned. There's no flow of carriers from one side to the other, which is naturally not the case, but this is just to give you first hand idea as to what might be happening. Okay, so again, just to reiterate, there are two discontinuities in this problem, in this heterostructure rather. First is your conduction band discontinuity, which you see naturally, as the name suggests, at the conduction bands between this heterojunction. Second, you see at the valence band. Okay, right. So same problem, this time again the same materials, just the 25% algan. So first I just need to determine the band gap of Eg1, so that will be 0.25 times band gap of aluminum nitride plus 0.75 times band gap of gallium nitride. I'm again ignoring the Boeing parameter, so this will be 0.25 times 6.2 plus 0.75 times 3.4. I believe we have calculated this came out to be 4.1 EV. Okay, again if I draw the same thing, again you can just simply say that delta E, the band gap discontinuities, which is nothing but delta EC plus delta EV, is nothing but the difference between the two band gaps. This is 4.1 EV minus 3.4 EV, which will be 0.7 EV. That's fine. Now let's just draw the diagram again. Okay, so again left side is your algan, right side is your GAN. This is the E vacuum or our reference level. Okay, so if I recall, that was 1.9 EV, the electron affinity. So and the other one was 3.1. So let me just see. So this is 2.2 divided by 4, so it will be 0.55. This is only 25% algan. So the electron affinity will be 3.55 EV for this structure. (3.55 EV), and the band gap we have determined is 4.1. So this is your EC1, EV1. This band gap is 4.1 EV. Okay, let's draw on the gallium nitride side now. The electron affinity there is 4.1.
How did you write that electron affinity?
Okay, so electron affinity for aluminum nitride is 1.9 EV. How do I know that? I just in my browser I typed the electron affinity for aluminum nitride. It showed me in fact I'll try to share the link. Yeah, I have the link with me. So in fact this was the link. Refer to this. This is my reference for this. Just you can have a look. Okay, in this aluminum nitride is 1.9. That's where my data is coming from. GAN is forgot 4.1. Yeah, GAN is 4.1 from this the sheet that I have shared, the data sheet that I have shared. Okay, so chi2, as I was saying, is 4.1 EV. Let's draw this level EC2, and the band gap is 3.4 EV. So let's again draw this band gap EV2. This is again EG equal to 3.4 EV. Again let me write the absolute values from the reference level. So this level will be at 3.55 EV, and this will be 3.55 plus 4.1, so this will be 7.65 EV. This level will be at 4.1 EV. This level will be at 7.5 EV. Okay, again we notice this is a type 1 or a straddling type, because you can see the top of EC2 is less than EC1 and the bottom of EV2 is higher than EV1. So again this is a straddling type. Now again let me form the junction, again ignoring the fact that there will be some Fermi level difference, right? And again you will see a very small kink here. So this is delta EC, this is delta EV. Delta EC, as you can see, will be 0.55 EV, and delta EV will be 0.15 EV, and thus delta EC plus delta EV will be 0.55 plus 0.15. This will be 0.7 EV. These are just the first hand calculations, by the way. Again, I'm reiterating that because it's of primary importance to have. That's a very big condition. Okay, right. So it turns out I cannot run away with the Fermi levels and I have to live with them. So if they are present, which they will be present, how will I deal with them? So now we are going to talk about this. In fact, this is I would this might look a bit overwhelming, so I'll try to go as slow as I can. Okay, and let's hope that I'm able to get the point across. So first let us draw our vacuum level. Okay, I'm going to start with the fact that we have the straddling band, so I'm going to start with that assumption, but this time I'm also going to add the Fermi levels. Okay, so let's do that. So this is my EC1, this is Chi1, EC1, and let's say my Fermi level for this fellow lies somewhere over here. Should be a solid line, EV1. So as you can see, EF is closer to EC. For this semiconductor 1, we have a p-type doping. Okay, let's consider the second fellow. Again, Chi2, right? This will be my EC2, and deliberately choosing considerable difference in the band gaps, and I'm assuming this to be n-type. So this the diagram on my left is before junction formation. Essentially what I'm going to do is now I'm going to bring them closer and closer together, but you can at least notice that it is a straddling type. We should expect something close to the straddling type of behavior for this heterojunction. Heterojunction, again I'm re-emphasizing heterojunction or heterostructures because the semiconducting materials on your left and right have different band gaps. Okay, now I'm very close to forming the junction, but as soon as these materials come into contact with each other, the average energy levels, which is EF1 and EF2, you can see that it's high in EF1, low in EF2, just like we in the PN junction, right? We had seen that. What essentially it means is that the electrons will now, I'm only talking about the electrons in this case to keep the discussion simple. So electrons naturally will try to flow, if it's possible, to the energy of to a state with lower energy rather. So what you can see is that the electrons will now leave the semiconductor 1 because energy is higher. This is essentially the average energy. So EF1 is it's a statistical construct. Yes, I know where the probability of finding the electron is half, but when you're using them in such schematics, another way to use them is just treat them as some sort of average energy. So average energy is higher here, average energy is lower, but this means that when you're forming the junction, again applying not any bias, no light shining, anything, at equilibrium EF must be flat, simple as that. So what's going to happen is that this fellow has to come down, on the left side has to come down, on the right side has to go up. But again, please remember, in the bulk EF will remain close to EV on the right side, EF1 will close remain to EC on the left side. So in the bulk on both sides, the situation will not change, just like we had in the PN junction, right? So depletion will form here in the sense that electrons will now start to leave this semiconductor 1 and they'll travel to semiconductor 2, simple as that. Now how and thus this energy, the average energy will get lowered in first semiconductor, and it will keep on gradually increasing in the second semiconductor until until an equilibrium is reached, that is EF1 is equal to EF2. So what I mean by that, just to denote there will be a lot of moving parts, so I'll try to keep it so this will tend to go down the Fermi level here, and Fermi level here will tend to not there actually, no, let's say
Near the surface.
sorry,
Near the surface.
yeah, near the
Or the
surface.
contact.
Yeah, that's what I was coming to. It will get too cluttered there, and so I was avoiding. But let's say I do not have much liberties here. Okay, so let's say this has to come down and this has to go up. Ultimately an equilibrium will be reached and EF1 will be equal to EF2. Also, which I denote in green, so the electrons, how is this being facilitated? The energy levels being, so the electrons are traveling from this side to this side. Okay, that is happening. Fine. And also this suggests that this is so this is an n type, so it will have excess of this is an n type material, so you can appreciate that it will have excess of electrons, and this is a p type material, it will have excess of holes. Again, only talking about electrons here, not holes. Fine. So let's just, so the way as Professor Digvijay explains very well in his video lecture, I'm just going to use the same logic there. What you do is you fix these points at the junction. These 4 points will not move. They will remain as it is. The rest of the band diagram will shift. Let's do that now. Okay. I'm not going to draw chi1, chi2 anymore, because now it's not standalone semiconductor, it is now a junction. Okay, so let me first just draw these 4 points that were there earlier. Okay, point 1, point 2, point 3 and point 4. These are the 4 points which are drawn. The purple color is what I have retained. Okay, second thing that you will notice that we must ensure is that the Fermi level will remain flat throughout. Okay, so let's say this is the Fermi level, so EF1 will now become EF2 equal to EF, which is this. Fine. First we'll do the simpler things first. In the bulk, the Fermi level on the left will be same gap as this, so EC1 will look something. In the bulk, it will start from somewhere over here like this. Okay, and the band gap is, if it looks like this, so band gap will not change naturally, so at least till this point of time I can draw. This is EC1, this is EF1, this is EV1. Let's draw on the right side also. So EV2, the band gap will be closer to this, so it will be look something like this. This is EF2, EV2, and again band gap cannot change rather. Okay, so what we'll have is something like this, EC2. Okay, so now we have taken care of the bulk and the Fermi level is aligned. Now what is happening is that depletion is happening. Okay, so what must be happening is that this point, top point corresponded to EC1, so now you will have a band bending like this. Similarly, you will have a band bending from this, because EC2, remember, was connected to the second point, which is over here, and I'll draw EC1 again because it looks a straight line. It's not the case. Okay, and third point was corresponding to EV2, so let's do that, EV2. Fourth point was corresponding to EV1. I've drawn EV1 a bit too further away, so let me correct this, because the bending will be the same for whatever is for EC1, the same will be for EV1, because the material has not changed. Okay, so this is how the new band diagram will look like, and this is the discontinuity which we had seen, which I had very conveniently in a different way I have written that. So this is your delta EC, the discontinuity in conduction band. This is our delta EV, the jump in EC and the jump in EV. Okay, and this is essentially the total band discontinuity that we write over here. Okay, now a few other things that I'll now like to point out. Which color should I use? Okay, so this is your depletion region now. This is your depletion region. Call this WN, because this is on the N side. Correspondingly, again, so this is your depletion region on the P side. Call this WP, measuring everything from the metallurgical junction. Okay, which was, again, if you draw vertical line joining these four orange points, purple points, you'll get the straight line, which is what I have drawn here. Okay, okay, so this the extent of the built-in potential, so we can write it as Vn, right? This will be simply be 2 times, sorry, not 2 times, let me just yeah, Q and T. Hold on. It will be Q N D Wn square over epsilon naught epsilon n. This is the similar trend that we had seen for PN junction. The derivation remains the same, and Vp, the potential, or this, let me call the same symbol, phi n and phi p, this will be equal to Q Na Wp square over 2 epsilon naught epsilon p, and the total built-in potential will be nothing but the sum of these two. Okay, that's the story that that I wanted to convey over here. There is one more thing, like how to find the band discontinuities. Okay, let me in fact write that here rather than doing this, because sorry about this. Okay, so I'll write these, what do I call them, the built-in potentials on the next slide, because I have a problem corresponding to that. I'd rather use this space to find, let's say you want to find delta EC. So how you do that? So it's a very simple thing to do. You start from here, and we'll also come to the same point, but on the other side. So first step, you go from here to here, you jump high, and then let's say this is starting position 1, you go to position level 2, then you go from level 2 to level 3, which is this level, then you come down from level 3 to level 4. So this is level 3, this is again level 3, this is level 4, right? And then you again jump from level 4 to level 5, which is this, the built-in potential on this side. So you jump from 4 to 5, and then finally you jump from 5 to 6, from 5 to 6, and then you jump from 6 to 7. Let's write this. From 1 you have to go to 7. What will the difference? 0, because this in equilibrium, Fermi level is flat. So let's try to write this transition from 1 to 2. How much energy you are gaining? EC1 minus EF1. This is the gain in energy, hence I'm returning is this way, plus this much energy, which I write it as phi n, the built-in potential on the n side when we grow from level 2 to level 3, this curve, minus delta EC, this jump, because we are coming down, hence the term minus, plus we reach the position 4. From 4 to 5 we have to go up, to go from 4 to 5, we have to go up, right? And what is the gain? The gain in energy is 5p, the built-in potential on the p side, right? And then you drop from 5 to 6, which is the band gap of on the semiconductor 2. So I write this as Eg2, and then you again gain this energy, which is Ef2 minus Ev2. This will be equal to 0. We know this because this depends on doping, right? You put in the expression n equal to nc e to the power minus e to the power ef minus ec over kt. You get this term because that depends on doping. So we know this term. We know phi n, right, because of the depletion width. ec is the term that we can determine, right? Is actually the term that we want to determine. So this is the term that we want to determine. Phi p is again just like phi n, we can determine. Eg2 is, we know what is the material, so this term we know. Again, this is the term, this is nothing but this is on p side, so we know again you apply p equal to nv. The second session we had talked about the carrier concentration in equilibrium. Okay, so again you write that and you can get this term. So from this you can get delta ec, right? Similarly, if you right now I have done the top half of this Venn diagram. If you do the bottom half, you can also obtain an expression for delta ev. In this way, we know experimentally how delta ec and delta how are the band continuities arising. Another thing, if you ignore phi n and what is it, phi p, again these are coming from doping. Earlier in the previous two problems I had ignored them, right? The bendings I have ignored, and Fermi level alignment. So if you ignore them, essentially you treat them as flat lines, and again the problem simplifies to an extent, but as I've been telling that this is this can be misleading in many instances. Okay, from this we can establish the band discontinuities on conduction as well as the valence band. Okay, we are almost out of time, and but I have just last question. So we have a heterostructure made of 25% aluminum arsenide, sorry, not aluminum nitride, and its doping is 1e16, right? And depletion width is given as 0.1 microns. And okay, so I'll write this. This is aluminium gallium arsenide versus gallium arsenide. This is n-type doped, this is p-type doped. Okay, and we need to calculate the built-in voltage. So first just we can simply this is extension of the which we are talking in the previous slide. So these are the expressions that I wrote, if you recall, and this is a heterostructure, aluminum gallium arsenide to gallium arsenide. Just that we need to put in all the expressions. Q is 1.6 10 to the power minus 19, nd is given as 10 to the power 16, and Wn, depletion width on the n side, is given as 10 to the power minus 5. Remember the units has to be centimeters because all of this is in centimeters. 2 epsilon naught is 8.85 10 to the power minus 14. Epsilon n must be given for L gas. L gas is actually not given, but gallium arsenide is given. Again, we can use the Vegard's law. So what will be the for L gas? It will be 0.25 times epsilon for aluminum arsenide, because aluminum mole fraction is 0.25. Okay, and plus 0.75 times epsilon of gallium arsenide. So this will be 0.25 times aluminum arsenide is, I believe, 10. Yes, this is 0.25 times 12. So this will be 2.5. Sorry, this will be 0.75. 2.5 plus 9. This will be 11.5. So you can write 11.5 here, and you can get this answer. I believe this is coming out to be 8.6 into 10 to the power minus 3 volts. Similarly, you put 1.6 minus 19, Na is 10 to the power 15, Wp is given this will be 2 into 10 to the power minus 5 whole squared, divided by 2 into 8.85 into 10 to the power minus 14 into, this time it will be simply 10. And so this will come out to be, 1.6 times 4 divided by 2 divided by 8.85, Okay, so this is coming out to be around 0.35 into 10 to the power minus 2 volts. What is the total built-in potential? Is nothing but phi n plus phi p. So this is 8.6. Let me add 0.86 to this. So this is coming out around 12 into 10 to the power minus 3, something like that. So this will come out to be I'm made somewhere a mistake of 1 second. Just a second. 8.6 by 1000 plus 0.035. Sorry, I have to do it again. I had done it earlier, but I'm getting the wrong answer. By 1.6 by 2 by 8.85 by 11.5. It's 7.86 or something. So this value is 7.86. This is 7.86 into 10 to the power minus 3 is there, so minus 3, it will come minus 6, minus 16, and this is minus 14, so it will be minus 2. Okay, so this is approximately 7.86 10 to the power minus 2, and this is approximately 1 order lower. Yeah, so so this will become 7.86 10 to the power minus 3, but it will get multiplied by so now I think it's fine. So 7.86 plus 7.86 divided by 100 and plus 0.035. Yeah, so this is actually 3.5 into 10 to the power minus 2. So final answer is coming out to be 7.86 plus 3.5, which is coming out to be 0.1136 volts. I mean EV and volts skew, you have to interchange, so this is the most correct option. Okay, here I'm just ignoring in the previous slide I talked about the band discontinuities. Here I'm just talking about the built-in potential on the N side as well as P side, the combined one. All right, so that is all for today. Thank you for staying back. Thank you for listening. See you again next week.